Yes, any questions about any of the things that we had covered until now? We were looking at the time evolution recently, how the states change with time. We had studied especially two problems. And on Wednesday we studied, for example, the neutrino oscillations, how the neutrino flavor changes with time. And it was basically because of the fact that what we call flavor doesn't commute with the Hamiltonian, it's not conserved. So since it's not an energy eigenstate, even if it starts as one flavor, let's say electron neutrino, it's not a stationary state, so it just becomes some other type of neutrino. Well, forget about the neutrino in that problem. And what we have is you have a given state, and that state in time changes its properties, unless it's a stationary state. So you can call that state a flavor state or a definite spin state, etc. As long as it doesn't commute with the Hamiltonian, it will be changing in time. Now, there was one thing that we had kind of skipped. What about the time evolution? We had said that this unitary operator, e to power minus I over h bar h delta t, or in infinitesimal form, u is equal to 1 minus I over h bar h, let's say dt, in general, it gives me how the state evolves in time. But the problem is most of the time it's quite difficult to evaluate this operator directly. So sometimes it's easier to solve differential equations. And sometimes it's the computers that can solve the differential equation. So it would be also nice to have some kind of a differential equation whose solution would allow us to either find this unitary operator u or to solve for our kets. So what will be our differential equation, so-called, we will be deriving first the Schrödinger equation. Now let's start with u. U of t, let's say u of t, t0, this is equal to e to power minus I over h bar h of t minus t0. This evolves my state from the time t0 up to the time t. Now we can obtain a differential equation for this one if we want. So just take the derivative with respect to t0. This will be minus I over h bar h e to power minus I over h bar h t minus t0. But this is nothing but my u. So I h bar d by dt of u is nothing but h times u. But just keep in mind, here we made an assumption. Do you see which assumption we made? We basically assume that h at different times commute. Well, as long as h at different times commute, this is the equation we have for the unitary evolution operator. Well, one of you had just said that h is time independent. That is also correct, that we started from this expression of u, which is valid only if h is time independent. But this final expression is valid as long as h at different times commute. Do you see where we made that assumption? Not really. You see, it's somewhere over there, but the derivative of e to power minus I over h bar, let's start by removing the assumption that h is time independent. From t0 up to t, h of t prime dt prime. I said that this is equal to minus I over h bar h of t e to power minus I over h bar from t0 to t h of t prime dt prime. This is valid only if h of t prime at two different times the commutator is 0. You see, to write such an expression, well, this expression makes sense in the form of a Taylor expansion. So that expression is actually sum from n0 to infinity 1 over n factorial minus I over h bar to the power n from t0 up to t dt1 dtn of h of t1 h of tn. Or let me write it in a slightly different way. H of t1 dt1 from t0 up to t h of tn dtn from t0 up to t. You see, we are taking the time derivative. So here we have n of them. So we are taking the time derivative of the product of n operators. Well, all of them are the same. So let me write it A. Now this is equal to dA by dt A n minus 1 terms plus A dA by dt A n minus 2 times plus A dA by dt n minus 1 times. So basically, that derivative contains n terms. I can simplify it if dA by dt commutes with A. If dA by dt commutes with A, I can move dA by dt to the front. In that case, they are all equal to each other. So this is equal to n times dA by dt, A, n minus 1 terms. If dA by dt A is equal to 0. I cannot do the last step unless that commutator is 0. Now, in my case, A is nothing but this integral from t0 up to t h of t prime dt prime. dA by dt is equal to h of t. So if I want to make this simplification over here, these two things should commute. Otherwise, I cannot make that simplification. And if I cannot make this simplification, then that the derivative of the exponential is just some factor multiplying the exponential is not true anymore. So that's one assumption I made. Now let's see how my kets evolve in time. So this is how my unitary time evolution operator changes with time. It's the Schrödinger equation for the time evolution operator in a sense. Now let's see the Schrödinger equation for my kets. You see, we had defined this ket at the time t to be this ket multiplied by our time evolution operator. So basically, I have this ket at the time t equal to t0. It is just alpha t0. This is my initial condition. And at a later time, my ket is given by this operator u, acting on my initial ket. Now let's take the time derivative of both sides. This is equal to I h bar d by dt u of t0 alpha t0. But keep in mind that the ket alpha t0 is independent of time. So it's only u that depends on time. So the derivative acts only on u. And I know how u evolves with what's the derivative of u? It's just h times u. So it just gives me the Schrödinger equation for my kets. This is equal to h times u alpha t0. But this is nothing but my ket. So the time derivative of my ket is equal to Hamiltonian times my ket. So this is the Schrödinger equation for my kets. I still don't know what the operator h is though. So what I'm saying is there is an operator which generates time translation, which we call h, whose form, well, we don't know most of the time. And in terms of this operator, this is what the time derivative of my kets are. True. Alpha t0 is time independent. It is my initial value. But then, so I'm taking the time derivative of u only, which gives me h times u, but now u I can act on my ket. Now I obtain the time dependent ket. You see, I have these two kets. One is this one. That is a time dependent ket. It's the ket that initially was at the state, it was equal to the ket alpha t0. That was the initial value. As time evolves, it evolved. Now it's a time dependent ket. But alpha t0 is just some fixed value, some initial value. It doesn't depend on time, t. Any other questions? Okay, so if you remember when we were discussing our neutrino oscillations, we had seen that the probability that the neutrino stays as a neutrino was equal to 1 minus some constant times cosine of delta E t over h bar minus 1. It was something like this, if I'm not wrong. And then we said that, okay, neutrino, even if you start with a state, let's say nu E, it deviates considerably from nu E if delta E times t was of the order of h bar. So you see, that is when the parenthesis has the largest value. So it deviates the most from the initial state at that time. Now let's make it somewhat more general. I mean, it's not special to the neutrinos. So what we will do is we will first define this quantity. You see, we have alpha t0. This is our initial ket. As time evolves, it will become alpha this ket. Now the question is how much this ket resembles its initial value. That is what we would like to look at. So this resemblance, we can just define it as this overlap integral. And in fact, let's just take its absolute value. Now, why did I take the absolute value? For example, if we have a stationary state, then alpha t0 t is nothing but e to power minus I over h bar e alpha t minus t0. A stationary state is basically a state that doesn't change in time. So that is a state which is an eigenstate of the Hamiltonian, and the eigenvalue, I just denoted it by E alpha. So for this state, this is just 1. So if this Ct is what we call the correlation function, we say that if Ct is 1, as in this case for a stationary state, the ket at an arbitrary time t is strongly correlated with the ket at the time t is equal to t0. If it is, let's say, 0, it just tells us that we started from a state, as it's evolving, it just became a completely different state. For example, we can have, initially we might have a state that is an Sx equal to plus h bar over 2 state. As time evolves, it might become a state that is Sx is equal to minus h bar over 2. So these two kets, their inner product is 0, so they just become completely uncorrelated. So this is what we mean by this correlation. So if this function c of t is close to 1, we know that the ket at the time t closely resembles our initial ket. If it deviates from 1, then we know that at the time t, the ket we have has no resemblance to our initial ket. Now let's see, this alpha t0, we can consider it as some kind of a sum. We can expand it in terms of energy eigenkets in general. Now, of course, if there are more than one term in the sum, it's no longer a stationary state. So let's see, this is Cn an, sum over n, where the Hamiltonian acting on these kets an are just En an. These ans are our energy eigenkets. Now, one advantage of this is now we know that how it evolves. So we know that if we expand our ket in terms of energy eigenkets, its time evolution is given by, with the same coefficients, each term just acquires this phase En t minus t0 an. So this is my ket at the time t. Now I can calculate this overlap, this inner product. This is equal to, well, the first bra is n Cn star an. The ket, sum over m Cm Em t minus t0. Since those summation indices are dummy indices, I just use two different dummy indices for each one of those sums. And here, of course, I have Am, which becomes sum over Nm Cn star Cm e to power minus I over h bar Em t minus t0. But that inner product is nothing but Kronecker delta Nm. If they are equal, then they are just 1. If they are not equal, it's 0. So this is nothing but sum over n Cn squared e to power minus I over h bar Em t minus t0. Now, for most practical applications, the energy spectrum is almost continuous. It's not discrete. Here we are assuming they are discrete, but they will be most of the time continuous. So we can also convert it to an energy integral. Now, the exponential depends only on the energy. Of course, we might have more than one state having the same energy. We can have degeneracy, or almost degeneracy, let's say, that we will parameterize as the density of states. Basically, rho E times dE is equal to the number of states, number of kets having energy in the interval E and E plus dE. And furthermore, we have those coefficients which depend on n. Let me just replace them with functions of E. So this is the magnitude of this one gives us CT. Yes. Well, you see, in practical applications, we will be studying, for example, particle in a box, which probably you're all familiar with already. So what do you remember? The energy levels of particle in a box is h bar squared n squared over pi squared L squared. No, pi squared is at the top. There's no degeneracy here. But let's see what is the difference in the energies between two nearby levels. This is equal to h bar squared pi squared over L squared times 2n minus 1, which basically goes to 0 as L goes to infinity. Well, of course, L is never infinite, but even for an object of this size, let's say, L is large enough, h bar is very small. L is large enough that you will not be able to really separate two different energy eigenvalues. In this sense, they are almost degenerate. Not exactly degenerate, but almost degenerate. Well, usually you take, you don't really excite your states. If n is very large, you see, the problem is, for a realistic case, you don't have infinite potential wells. You have finite potential wells. Now, if n becomes large and large, the particle just escapes from the well, because you are also increasing En faster. En is proportional to n squared. Before n becomes large enough so that delta En becomes significant, En becomes so large that your particle is no longer in the well. So such large values of n are not realistic, let's say, for this simple model. Of course, for a more realistic model, let's say, what you would have is you don't have these are just the infinite potential well problem. This is a good approximation as long as your particle is at the bottom of the well. As the energy of your particle gets larger and larger, it's not a good enough approximation. You have to make more realistic approximations. And most of the time, the potential wells we have basically have this form. You see, as n increases, effective value of L also increases. We don't need to do anything. So you are right. If you just take this expression at its face value, delta E n need not go to 0 if we first take the limit n goes to infinity. If we first take the limit n goes to infinity, then delta E n goes to infinity. But that limit is not physical. So let's go back to this case. Well, Ct is basically the absolute value of this one. Now, let's see. Most of the time, the Ce, okay, some bad notation. Let me change these expansion coefficients to D. Most of the time, this function dE, if you try to create an energy eigenstate, for example, it will have this form. This is E. This is my function dE. It will have some maximum value at some energy E0, the state that you are trying to create. But it will nevertheless have some width. This is our delta E, the uncertainty in the energy that you create, of the energy of the state that you create. So C of t just becomes the absolute value of e to the power I over h bar E0 t minus t0 dE e to the power minus I over h bar E minus E0 t minus t0 rho E dE absolute squared. But our Ct is just the absolute value of this one. This number has absolute value 1, just multiplying with it or not doesn't really make any difference. So I can just write it as dE rho E e to the power minus I over h bar E minus E0 t minus t0 d squared. So this is my Ct as a function of time. Now you see, let's look at this expression over here. Now E minus E0. First of all, we already claimed that since dE has this form, in this integral, only the terms for which E minus E0 is around delta E contributes. Because otherwise, dE is 0. If E minus E0 is not typically around delta E, that is, if E is further away from E0, then dE just goes to 0 because of the way we are creating our state. Now, even if E minus E0 is typically around delta E, you see that exponential over there. That exponential fluctuates. It's an oscillating term. But if it's an oscillating term, if t minus t0 is very large, that term will be oscillating very fast, which basically means that that exponential for very nearby values of E will get positive values and also negative values for almost the same value of E. But if the other functions, rho E and dE, they do not change fast. So if you have rho e dE, which doesn't change fast, multiply it with a function that changes very fast between positive and negative values, and when you sum them up, well, positive values and negative values will just cancel each other. Again, you get 0. So that is, if t minus t0 times delta E is very large, much, much larger than h bar, in that case, C of t will typically be 0. So your state is now completely different. Now this t minus t0 is what we call delta t. So typically what we have is our state stays more or less as itself as long as delta E times delta t is around h bar. Now look at this function. Let me just take the real part, for example. Well, we are integrating over delta E, so let me just plot this function as a function of delta E. Now, let's say delta t is equal to 0. What will be the function? It's just 1. This is the case when delta t is equal to 0. There is no oscillation. Now, let's say delta t has some value. Let's say delta t is 0. It oscillates between 1 and minus 1. Let's say now we have delta t1, which is much larger than this delta t0. It now looks like this one. This is delta t1. Okay. Now, of course, this is just the real part of that exponential. Now, let us multiply it with rho e times dE. Let's say it's a function of e. This is my E0. This is rho e times dE squared times cosine delta E over h bar delta t. Well, when delta t is equal to 0, it's just dE, which is peaked around E0 times rho e, which gets larger as E increases. Well, it will have typically such a form. This is when delta t is equal to 0. Its integral is definitely non-zero. Let's just now take the case that the delta t is delta t0. Yeah, it will be oscillating somewhat. It will have this value, this shape. Well, when you take the integral, you see that there are positive parts and negative parts. They will be canceling each other. So typically, it will get smaller and smaller, the integral. Well, there might be an exact cancellation. Maybe there won't be an exact cancellation. We don't know. But let's see if it gets even larger. This is delta t is equal to delta t1. Now, Now you see that here it has a large negative value, here it has a large positive value, and those two values are more or less the same. So when I sum them up, which is an integral, they will cancel. So you see that its value for delta t is equal to delta t1 is smaller than its value for delta t is equal to delta t0, which is definitely smaller than its value when delta t was equal to 0. So that is why if this delta t times delta E is much, much larger than h bar, this over this inner product that we call Ct, it just goes to 0. So my state stays as it is only if delta E, which is the uncertainty in the energy of my state, times delta T, the amount of time that I allowed my state to evolve, this product should be something around h bar. So if you create, for example, an energy eigenstate or a stationary state, for that state delta E is 0. So in that case, delta T can be infinite. So my state stays as it is for an infinite amount of time. Well, that's how we define the stationary state. But unless we can create a stationary state, well, most of the time we cannot really. How do you test a stationary state? How do you test that a state is stationary? Well, how do you take an infinite time interval? Yeah, large enough. That's not infinite. So basically what you do is, for practical reasons, you have some amount of delta T. But that also means that you can only be sure that your state is stationary within an error bar of delta E, given by this relation. So basically this also tells you that you cannot really create an energy eigenstate in real life for practical applications.
Orada oscillation yok.
Okay.
Ama şu an bahsettiğiniz stationary state oscillation olmadı.
Well, you see, what I call this delta T is I create my state, I look at my state at a later time. Okay? Now, delta T is equal to 0 means I create my state and I straight away look at it. That is delta T is equal to 0. How much does it resemble my initial state? Perfectly. There's no evolution. Okay? So what is the uncertainty in the energy of my state? Well, it can be infinite. I cannot really say anything. Because, for example, if I want to say that my state is stationary, what I should do is I should start from one state, and for a long time it should stay in the same state. Now, whatever superposition of energy states I have, I can add kets with any energy. If I measure it right away, I will observe the same ket. So the only thing I can say if delta T is equal to 0, when delta T is equal to 0, is that delta E is infinite. It can be, well, it can have any, the components that I'm superposing in my kit can be any energy eigenvalue. So that's what it means when delta T is equal to 0, there's no oscillation. So whatever superposition I have, it will not evolve. So I cannot really say anything about the spread of the energy. If I want to create an energy eigenstate, for example, I have to create it now and look at it at a later time. How much did it change? And if it doesn't change within that amount of time, even then I cannot really say that it's a stationary state. Because still that state can be a superposition of states that have an energy spread of delta E, given by h bar over delta t. Such a state will not change in that time interval. To be able to observe any changes in my state, in that state I have to wait longer. And to make sure that there is no delta E, I have to wait an infinite amount of time. Well, there are a couple of things that you have to pay attention to, though. For example, we had derived this relation. Delta x squared, delta p squared is larger than or equal to h bar squared over 4. Well, we rigorously derived this. We made a precise definition of delta x, we made a precise definition of delta p, and we have this strong statement that this product has to be larger than or equal to h bar squared over 4. But in this new uncertainty relation, for example, I don't put a larger than or equal to sign. Or in fact, I don't even put any specific sign, because this is just order of magnitude estimates. So there is no precise definition of what delta E is or what delta T is for a given state. That is why you will see in some places that it's h bar over 2, in some places h bar over 4, or h bar or 2 h bar. It doesn't really make any difference for our claim. So these two uncertainty relations, let's say, they have different natures. And furthermore, for example, delta x and p, we call them operators, but t is not an operator. So we cannot even if we want, without an operator for time, we cannot really define this delta t without this time operator. Any last questions? Okay, let's give a break now, because after the break we will continue with a new subject. So a 10-minute break. So see you after 10 minutes.